In this video we will look at how to render dynamic point clouds with Niagara in the Unreal Engine 4.25. We use this, for example, in the visual computing group of the University of Bremen in some VR simulators. Thanks to Thomas Höring, who came across with this method for point cloud rendering. The version I present here is somewhat simplified and generalized. Sorry for my somewhat monotonic voice that follows and probably some mistakes in the English language, but it turned out a bit later than I hoped when I recorded the voiceovers now, and I'm just happy to be done with it. But I think it can be helpful for some people, so let's start from scratch in the first person template. In the beginning, create a new folder and call it, for example, point cloud. In this folder, create a new Niagara emitter and just call it point cloud emitter. In the emitter properties, activate local space, select the GPU for the simulation target and define a bounding box which is so big that all points will lie in it. Let's make some changes so that the point cloud will not be recreated all the time and the single points will not be killed and exist permanently while the game is running. For that, we also should deactivate the lifetime and should not kill the particles when the lifetime is over. Now we add the spawn burst instantaneous module, which creates the number of points we want. Because we want the number of points to be variable, we create a new user exposed variable of the type int32 and call it point count. Now we propagate the value of the point cloud variable to the spawn count parameter of the spawn burst instantaneous module. Because we save the position and the color information of every point in a texture, we have to assign a unique ID to every point so that we can use it to generate the UV texture. For this, we create a new module which writes the execution ID into a new variable of each point. Now we have to create a module which reads the position and the color of each point from the textures and save this information into an attribute of each point. In this module we create 4 inputs. 2 of them are textures and 2 of them are the size of the textures in pixels. To generate the UV coordinates, we also have to use the point ID, which we set in the previous module. The UV coordinates are now generated in a way so that every point ID is assigned to a unique pixel of the texture. For that, we calculate the modulo of the point ID and the texture width so that we get always an integer in the range of 0 and texture width, and divide this value by the floating point texture width to get a float in the range of 0 and 1. To avoid artifacts, we add the size of half a pixel to the result so that every time exactly the midpoint of the pixel is sampled. That was the U coordinate. For the V coordinate, it's very similar, but instead using modulo, we do an int division by the texture width and use for scaling the floating point texture height. After we generated the UV coordinates, we can sample the texture and read the values into the position and the color attributes of the points. Let's also add this module to the emitter. Additionally, we have to create user-exposed variables for the module inputs of the Apply Textures module so that we can set these textures via C++ code later. At the end, we also have to create a Niagara system from the emitter so that it can be placed in the level. Now it's time to create the C++ class, which will create the position and the color textures dynamically, generates data for the point cloud, and writes this data into the textures. This class will also create the instance of the Niagara system, sets the user-exposed variables of it, for example the textures, and place it into the level. Because of that, we will make it an actor which will be placeable in the level. To be able to use Niagara components, we have to add it as dependency in the uproject file of the project. At first, let's include some header files which we need. Declare a destructor. And then we declare a variable and make it editable in the Unreal editor so that we can place the Niagara system in it. Additionally, we create variables for the generated data and a runtime variable, which stores the time the actor is placed in the level. The last thing we need is an Unreal-specific variable which describes the area of the texture we will update each frame. Let's switch into the C++ file. Here we initialize the texture size. In this example, we simply use about 1 million points. Also, the data arrays have to be initialized. For the position vector, we use floats for every coordinate, and for the color, we use 8 bits unsigned integers for each channel. In the destructor, we also have to delete the position and the color arrays. Let's create a little helper function so that we can set the user-exposed textures a bit more simple. In the beginPlay method, we now create the instance of the Niagara system and place it into the level. Here I choose 300 for the set position because the floor of the first person template is above 0. We have to set it to see the point cloud. For the rest, just use default rotation, scale, and set the other parameters. Now the textures have to be created. For the position texture, we create a float texture with 4 channels. To avoid interpolation of the texture coordinates, use the nearest filter. For the color texture, we use simply 8 bits per channel. Now let's assign these textures to the user exposed variable and set also the value of the other user exposed variables. Also initialize the runtime. In the tick method, we now generate some example data for the point cloud and upload it into the textures. This parameter is the size of a row in bytes. 16 bytes here because we use 4 floats per pixel. The update texture regions function expects a 8-bit unsigned integer pointer, so we need to cast our array pointer to it. This seems to be obviously a bug with the color texture. Yeah, here has to be the color race, not the color texture. Now we see our example point cloud, which we rendered semi-transparent with the default material of the sprite renderer in the Niagara system. Let's scale the point cloud a bit along the x-axis. If we activate the FPS display, we see that this is a bit slow. This is mainly because we call the sine function about 2 million times in each frame. So let me just pre-calculate the sine values at the beginning and only update the set position in the tick method to make it faster. There we are. By the way, this runs on a GeForce 2060 Super and an Intel i5 4750, while screen recording is activated. Let's change the color. For example, you can also change the size of the splats. By the way, keep in mind that you should activate sorting for the splats in the sprite renderer when you use semi-transparent points, otherwise you can get some artifacts. Or we can just use cubes instead of splats by using the mesh renderer. If the points also should cast shadows, simply call setCastShadows with true for the renderer instance in the C++ class. Yeah, the shadow seems not to be perfect, but I think this is enough for a proof of concept. The project file is attached if you want to use it. I hope you liked it.